Okay, we're gonna get started. So last time we finished up on the chapter that involved reactions and classifying reactions, and we're gonna kind of move on to a few different topics from a few different parts of some different chapters. So a little bit of 5, 6, and a little bit of 10 as well. We'll talk about some concentrations. We're going to talk about stoichiometry, molarity, concentration, and we'll talk about titrations, which is obviously the lab that's coming up here. Pretty formal lab and a 4-day lab, I think it is, as we have coming up. So we're going to start with stoichiometry, which obviously is putting together some of the topics from the previous chapters where we talked about grams, moles, molar mass, and also obviously balancing equations. So we're going to do a talk about stoichiometry, which again will deal with really calculations from the equation. And we do these calculations from the balanced equation, and it does help us sort of understand what we can produce in terms of a reaction. So some of the questions that stoichiometry tries to answer is, for example, if you started with a certain mass of reactants, how much products you could produce. It could also answer questions like if you produce a certain amount of product, how much of the reactants you needed to basically start that reaction and produce that much products. And when we talk about stoichiometry, as we will talk about, it really does relate everybody in the reaction. So we know we have reactants on the left-hand side, we have products on the right-hand side. And one of the things sometimes people have a misconception about when they're doing stoichiometry, for example, is a lot of times people think that it does has to perhaps always involve kind of going across the sort of arrow to the other side in terms of relationships. But really, stoichiometry allows you to relate everybody in that equation to each other. So we can definitely figure out something on the product side if we know something about the reactant side. We could definitely figure out something on the reactant side if we know how much products we produce. But also remember that stoichiometry can be done on the same side of the arrow. So you could do it between two reactants and understand the relationship of how much of one reactant you would need to add to another one. We could also do it on the product side as well. So we could also understand, for example, if we produced a certain amount of one product, we could also use stoichiometry to figure out how much of the other product. So again, sometimes people think when we talk about stoichiometry, we'll get into sort of the inner workings of it in just a second, but they do sometimes think it always has to kind of go from like one side to the next, and it doesn't. You can basically relate everybody in the chemical equation to each other through this type of calculation. So let's talk a little bit about an equation, and as we will definitely talk about as we go through this, you always want a balanced equation, and that should always be like your first step. Always when you have an equation, you should always make sure that it is balanced. And remember, as we talked about in the previous chapter or so there, when we balance the equation, we do only change the coefficients. And again, those are the numbers that obviously are in front of the formulas. And those coefficients are really the basis of stoichiometry and stoichiometry sort of calculations. And we can use those coefficients as a couple of different ways of looking at them. We could say that there are two atoms of magnesium react with one molecule of O2, gives us two formula units of magnesium oxide. Remember, sometimes they will use formula units for ionic compounds. Uh, the mole to mole relationship here is really the one that we use in stoichiometry, and it's really the one that we will focus on, obviously, in our stoichiometry calculations. And we could say that 2 moles of magnesium react with 1 mole of oxygen to form 2 moles of magnesium oxide. Again, here, there is no really magical trick to this. It is simply just our coefficients from the balanced equation. That is where we get those relationships from. The last relationship we won't use a lot, but it is the conservation of mass. And That is, as we talked about in a chemical reaction, the only thing that we do is really break bonds and make new bonds in most cases. So if we started again with, say, 4 carbons on the left-hand side of the arrow, we should end with 4 carbons on the right-hand side of the arrow. They may just be in different formulas or compounds, but because carbon on the left-hand side of the arrow is 12 grams and carbon on the right-hand side of the arrow is 12 grams, we have the same mass in terms of our elements of reactants and products. The one relationship that we do not use in sort of stoichiometry or any type of relationship from the equation is like a gram to gram relationship. So we don't do that. We don't look at those as how many grams of each of those. So it really is the mole to mole relationship that we use. And really, stoichiometry really just boils down to, it is really just a conversion factor. And instead of looking up in a table, for example, to find your conversion, we actually use the equation as our conversion factor. And that is because usually in these type of problems, we're given information about somebody in the equation we're not interested in, and we need some way to go from, say, our reactant to our product, and we use stoichiometry to do that. We're going to talk about 2 types of sort of stoichiometry problems here, and we'll see many more as we continue on through other chapters. But we're going to first talk about sort of basic stoichiometry problems. And basic stoichiometry problems pretty much have 4 steps that if you follow sort of in those orders, you will essentially should bring you to the right answer when it's all said and done. 100% of the time, step number 1 is you want to make sure you start with a balanced equation. And again, like I said, if you do not have a balanced equation, your whole mole to mole relationship and conversion is going to be wrong because it's not balanced. So remember that if you are given an equation, you should maybe take a moment and double check that it is balanced. You should take a really hard look at it if you do not see any numbers in it. If you do see some numbers in it as coefficients, you should double check that it is balanced. Also remember, as we talked about in the chapter when we were doing balancing equations and writing equations, you want to make sure that if you are given something in words, that you do start with the right formulas first, and then you balance. And as we also talked about, maybe even if you need to complete the reaction, if you have something like H2SO4 and a little sodium hydroxide, remember that when you do that, you want to get the correct formulas first and not worry about the balancing and then come back and balance. So again, when you're trying to predict what are my products on this side, we want to just think of the basic units of each of these, the basic ions, and we do want to put it together properly, just like you were doing nomenclature. So remember, in this case, we will take our double displacement, so we're going to switch partners. So H plus and OH minus, that is going to give us our water. And here again, when we put this properly together, Na is +1 and sulfate is -2, which means we will need Na2SO4. So I ran out a little bit of room there. But at this point, once you do have the proper formulas, then you should go back and balance. Remember, you never want to kind of balance and write the formulas at the right time, because as we talked about, you essentially will end up with the wrong formula and it won't balance and everything will be incorrect. And obviously we need to put some 2's around here probably to balance that up, and we'll be in good shape. The next thing, once you have it balanced, pretty much in a basic stoichiometry problem, we'll pretty much be given just one piece of information. It could be a piece of information about a reactant. It could be a piece of information about a product. Whatever piece of information they give you in terms of a number or value, you essentially want to get it to grams. So you want to get that thing to grams. Again, that may require a conversion from some other unit to grams. But once you have everybody in grams, you then want to do our grams to moles conversion. And a reminder that our grams to moles conversion involves the molar mass from the periodic table. So we're going to use the molar mass as a conversion factor. grams per mole to convert to moles. So definitely a lot of times in basic stoichiometry problems, grams to moles, again, using the molar mass from the periodic table is usually your kind of second step in your stoichiometry problem. The third step is actually the big stoichiometry move, and that is when we do go to the equation and we basically find the two things that we're interested in. One thing that you're interested in is whatever they gave you. So whatever number you pretty much converted into moles in step number 2, you're interested in that. And whatever you're trying to find is basically the other thing that you're interested in. And again, we're going to use those coefficients as the mole-to-mole relationship to allow us to do a conversion from what they gave us to what we're interested in. And the last step, oftentimes, I would say in this class, you're not usually asked to give your answer in moles. Sometimes you may, but a lot of times you do need to convert it to some other unit at the end of the calculation. So you usually will have to take it from moles back to some other unit. I will say that probably in a lot of cases, you will go back here at the end, moles back to grams. So sometimes you'll use molar mass to do that. In later chapters, and even in this chapter towards the end when we start talking about it, we may use things like molarity as well at the end to maybe figure out a volume. And it can be a wide variety of things. You could even use a gas law when we get to the gas chapter and maybe figure out something to do with a volume of a gas. But for the upfront here, kind of simple stoichiometry problems, very common at the end, moles back to grams using the molar mass. Any question on those stuff? Yeah. Why can't you go from grams A to just direct across there, grams B? You do because you need that mole-to-mole relationship to go from one reactant, for example, to the product, because you need a relationship based on the equation to figure out, if I have this much reactant, how much product I would get. So to maybe answer your question as well, let's take a look at an actual equation here, and let's talk about really the relationships that we can get from this equation. So when we have a balanced equation, what we want to look at again is all of the stoichiometric, they're sometimes called equalities, and they're equalities just like kind of regular conversion equalities, and they come from the equation. So if we look at this equation here, a little 3H2 and 1, obviously if there's nothing written there, it's 1, and our 2NH3, we could get several different relationships, right? We can have 3 moles of H2 needs to react with 1 mole of N2. And again, that is the mole-to-mole relationship. That is what is known as an equality here based on the equation. Now, clearly, when we look at it, 2 or 3 does not equal 1, so they are not equal to each other in terms of numbers. They are equal to each other in terms of proportion. Like if you're making cookies, right, you got to throw in there so much flour, so much chocolate chips, butter, and all that to get a dozen cookies out, right, when you make it. So when we think of these as being equal to each other, we want to think of them as being equal to each other in terms of proportion. We could also say that for every 1 mole of N2 we put in there, we will also get out 2 moles of NH3. We could also say that for every 3 moles of H2 we put in there, we could get out 2 moles of NH3. So from this one equation, we have really 3 equalities. And just like any equality, we really could come up with conversion factors to use. And conversion factors, right, are just our fractions that we get. So from this equality here, we could say we have 3 moles of H2 over 1 mole of N2, or 1 mole of N2 over 3 moles of H2. From this one, we could say we have 1 mole of N2 over 2 moles of NH3, are 2 moles of NH3 over 1 mole of N2. And lastly, from this last one here, we could say 3 moles of H2 over 2 moles of NH3. Or we could flip it around and go 2 moles of NH3 over 3 moles of H2. So from this one sort of balanced equation, we actually have 6 conversion factors that we could use in a particular problem. Will we use all of them? The answer is no, we're not going to use them all. We're going to use the ones that we need. Yeah. Correct. This is sort of, if you want to think about like the proportion of each of those, is you kind of need to throw in there to kind of make this reaction come out on the product side and produce those kind of 2 moles of NH3. Now, to, for example, illustrate your question earlier, why we can't, for example, go directly, say, from one thing to the next. Let's just say, for example, here that we were given or told that we produced, we'll go with 12 grams of NH3, right? And we want to know how many grams of H2 did we actually start with, right? So if we think about our calculation here, right, our 4 steps is we want to balance the equation, which obviously is done here. The next step is we want to take whatever they gave us and convert to moles, right? So the only piece of information they gave us was about NH3 in this reaction. So that is the only piece of information. So if we just think about where we are located, we basically only know information about that guy. But ultimately, where we want to end up is way over here, right? We want to basically end up knowing some information about that guy. So there is no way using just the information of the 12 grams of NH3 can we directly just go right on over to that H2, because we cannot use, as we saw on that slide, these are not a gram to gram relationship. So we can't use that as like a gram to gram relationship. So the relationship that we can use is that mole to mole relationship, which is all these possible sort of conversion factors that we could use. So let's just go through this problem here again, just to show you the 4 steps. So we obviously have balanced the equation. In this particular case, we do need to convert to moles. A reminder that if you're going through these sort of 4 steps, if something is done for you, don't go backwards, just go forwards in the step. Sometimes people are like, it's in moles, so let me unconvert it just to reconvert it back or something like that. So you don't want to kind of go back and forth. So obviously here, we're going to do our second step, which is convert to moles. And that means that we will need to go to the periodic table there to get the molar mass of NH3. So if we take a look at the periodic table, we go find our friend nitrogen. It says 1401 underneath it. We find our friend hydrogen, 1.008 basically underneath it. So we're going to calculate our molar mass here for NH3. So that is 1 nitrogen at 1401 grams per mole. Plus there are 3 hydrogens, each at 1.008 grams per mole. And that is going to give us a molar mass here of 1703, right? Very good. Yeah. So we're going to have 17.03 grams per mole. Remember that we basically could use molar mass as a conversion factor, so we could definitely use it like this with grams on top, moles on the bottom. But really, when we take a dimensional analysis approach to most of our calculations, we could flip it around, obviously, here and use it in the opposite direction as well. So we'll start here with our 12 grams of NH3. Remember, when we do dimensional analysis, opposites cancel. So although it is not written as a fraction, we can see grams are on top. So that tells us in order to get rid of grams, it needs to go in the opposite location. So in this case, we actually would want to kind of flip our molar mass around. and put it with 1703 grams per mole of NH3. Remember that when we do dimensional analysis, everything on the top gets multiplied, everything on the bottom gets divided, right? That's going to get rid of our grams of NH3. So we'll take our 12 divided by 1703, and that's going to give me 0.70464. I'm not going to round too much because I'm not done with the calculation, so I'm just going to keep a few extra digits there so everything is okay. So we have now balanced the equation. We have basically converted what they gave us into moles, and really the whole purpose of that second step is to set you up for the third step, which is really the stoichiometry step. Now we have a way, because we now have our number in moles, that we can use our relationships here to go from moles of NH3 in this case to moles of H2. So that is sort of the bridge that's going to allow us to convert from one to the next. So we do want to go to the equation, and like I highlighted here, we can see from the equation 2 moles of NH3 gives us 3 moles of H2. It is this relationship here that we saw earlier that gave us an option here of 2 conversion factors. So once again, always take that dimensional analysis approach. So let me actually just move it to the next page there. So we have 0.70464. 464. So this was the number we just got on the previous step there. I think I went to there, and we'll go here. And these are moles of NH3. So the moles of NH3 are up on top, and obviously here to get rid of it with dimensional analysis, we would need the moles of NH3 to be on the bottom, and we would want to choose this here as our conversion factor, our stoichiometry step here. Once again, like I said, you're not going to use them all. You're just going to use whichever one works. So in this case, we would do our third step, which is really our stoichiometry step. And again, if you help, just put it over 1. And now you know opposite, I need to put my NH3 on the bottom. And again, that is 2 moles of NH3 on the bottom. And 3 moles of H2 on top. Again, this comes from our balanced equation. That is the stoichiometry relationship. It is really just the conversion factor that's going to allow us to go, in this case, from our product back to our reactant. Again, we're multiplying the top, dividing the bottom. Our moles of NH3 are going to cancel. And if we do that, we're going to end up with timesing that guy by 3, dividing it by 2. We will now end up with 1.0570 moles of H2 in this case. So again, from the equation, we get that conversion factor to figure out our moles. Any questions on that so far? But in this particular example, we are not looking for moles, right? So we are looking for grams. So we do have to go one more step here to figure out how many grams that would be. And that is the fourth step, which is, if you did the third step correctly, you should be in moles. And we're now going to want to take this to grams. So again, we will need the molar mass here to do that. It is also really important to remember that we have now successfully gone from NH3 to H2 in this case. So we're no longer with NH3. So we do have to go back to the periodic table and calculate the molar mass of H2. And in this particular case, that would be 2 times our 1.008 grams per mole. Can give us 2.016 grams per mole as our conversion factor. We'll take our number here, and if I write it right, that would be even better, 1.057 moles of H2. Again, taking the dimensional analysis approach, moles are on top, so we do need moles on the bottom. 2.016 grams of H2. Moles are going to cancel, multiply, and divide. So that's going to yield us here 2.13 grams of H2. And again, at this point, I would clean it up to the right sig figs. Probably the right sig figs in this case is going to be based off of the only number that we had, right, which is 12.0 grams. That is all multiplying and dividing when we do dimensional analysis. So we're looking at the lowest number of significant figures. So again, if you follow these 4 steps in a basic stoichiometry problem, you'll be in business. It should lead you to the end. Now, clearly here I did it broken up step by step. I got an answer after each step, which is perfectly fine to do. I would again remind you, you never really want to round a lot until the very end. So you want to keep some extra digits so you don't have any rounding errors. But you absolutely could just combo all the steps together, and you could have went from obviously here to here and to here all in one sort of calculation across without getting the answer in between, and that's obviously perfectly fine as well, whichever way works better for you. And again, if you do get individual, I would just make sure not to round too much. Any question on those steps there? What does this number mean? This number means that based on the 12 grams of NH3 that we got out in this reaction, we would have had to put in there 2.13 grams of H2 to produce that 12 grams. We also could have, at this point as well, for example, we do know the moles of our H2. If we want to also figure out how much N2 we would have to put in there, we could also do a mole-to-mole relationship between those two and also figure out, how much of the N2 we would want to put in there as well. Any questions on that? All right, so why don't you try one since I did one? Why don't you try this one? And let's just say we started with we'll go with 1.25 grams of PbNO3 here. And we want to know how many grams of PbI2 would we form in this reaction. I'm going to give you some numbers that might be helpful in case the Dodger symbol over there covered those important elements there on that periodic table. We got Pb there, which is where we have there 207.2. We have our nitrogen 1401, our oxygen 16, and sodium 2299, and lastly our I here maybe might need 126.9. All right, so take a few moments there and calculate how many grams. Again, follow our 4 steps, balance the equation, convert to moles, do your mole to mole ratio, and our moles to some other unit. Okay, so let's take a look, see how you're doing. So again, we have a problem where we are given basically just one piece of information over here for our lead 2 nitrate. We want to get all the way over there to the other side for our lead 2 iodide. So this is definitely a stoichiometry problem. Also because really we're only given one piece of information, That definitely tells us it's just a basic stoichiometry problem. And when you see that, you really should just roll to these 4 steps. Even a more complicated one, you could roll through these 4 steps as we'll talk about. So clearly the first thing we want to do is balance the equation, and I don't see any coefficients, so I definitely should take a pretty good look at it to make sure that it is balanced, and it is not. We also see that we do need to balance it. We do have a polyatomic ion on both sides. So as we talked about when we were doing polyatomic ions, or have equations with polyatomic ions, sometimes it's much easier to keep those together to balance. So that's how I'm going to approach this. I got 2 nitrates on the left, only 1 on the right. So that tells me I probably should put a 2 here. Remember that kind of when you do this approach, although that balances the nitrate, you then want to go to whatever that's attached to. So in this case, it's attached to sodium, which is 2. And we then want to then put a 2 over here. That gives us 2 sodiums and 2 iodines. And that's good because we do need 2 iodines over here. And now we're balanced. We also have 1 lead on each side. So remember, it's a lot easier to balance sort of polyatomic ions by keeping them together, sort of balance them as units. Any questions on the balancing part? All right, step number 1, check. Next thing we want to do is take whatever they gave us, which obviously in this case is the 1.25 grams of lead to nitrate, and we want to convert it to moles. So we will do that. In order to do that, obviously, we will need the molar mass to go from grams to moles. And we'll go to our periodic table here, and we will see we have 1 lead at 207.2 grams per mole. Remember, we do need to multiply that 2 in here. So we will have 2 nitrogens at 1401 grams per mole, plus 6 oxygens at 16 grams per mole here. And that's going to give us our molar mass here to use. And we will have 207.2 plus 2 times 14.01 plus 6 times 16. Looks like 331.2 grams per mole. Really, again, our molar mass here is just a conversion factor to really put the units that we were given into the proper, or the value we're given into the proper units. So 1.25 grams of our lead 2 nitrate. Again, taking a dimensional analysis approach, we're going to end up with 331.2 grams on the bottom, moles on the top. Remember, again, opposites cancel. That's going to cancel out our grams and leave us with moles, which is what we're looking for. Divided by 331.2, going to give us 0.00377 moles of our lead to nitrate here. Any questions on that so far? Really, again, as we mentioned, the purpose of this step is really just to set us up so that we can now do the stoichiometry part in the equation. So we're going to do the 3rd step here. And again, we want to look at the 2 things we're interested in. So clearly in this case, we are interested in the lead 2 nitrate, and we are interested in the lead 2 iodide here. And from the equation, I picked apparently good ones here. It is a 1 mole of lead 2 nitrate will produce us 1 mole of PbI2. So remember that this is the relationship that we could get from the coefficients that are written there. And obviously, if there is nothing written, it does mean, like normal in chemistry, 1 for each. That's going to give us really 2 conversion factors to use. 1 mole of the lead 2 nitrate over 1 mole of the PbI2, or 1 mole of the PbI2 over the 1 mole of the lead 2 nitrate. So continuing on with our number here, and again, I didn't round too much there, so we're going to go with 0.00377 moles of PbNO3. Remember, again, opposites cancel, so the lead-2 nitrates on top. So to cancel it correctly, we will want to use the one on the right-hand side. It has our lead-2 nitrate in the opposite location, which is on the bottom there. And we'll go with 1 mole PbNO3, 1 mole PbI2 in this case. So that is going to cancel out our lead-2 nitrate. Again, this comes from our balanced equation. That is, again, really the big stoichiometry step here. I could probably do it without the calculator. We'll go with 0.00377 moles of PbI2. Any questions on that so far? Now, obviously, if our question was how many moles, we would be done. We could put a box on it, but we do want grams in this case. So we do have to do the fourth step, which is to take those moles and convert them to grams. So step number 2, step number 3, and now we're off to step number 4. Once again, we're going to go from moles to grams. So we're going to need the molar mass. And a reminder that we're no longer using lead-2 nitrate. We have converted to lead-2 iodide. So back to the periodic table here to get our molar mass. So we have 1 lead at 207.2 and 2 iodides at 126.9 grams per mole. That's going to give us a molar mass for PbI2 of looks like 461, I think. If I punch that in, just double check. Yep. 461 grams per mole. Again, that's going to be our conversion factor here on the last step. I'll write it over here in the middle so it'll be easier to see. We'll go 0.00377 moles of PbI2. Once again, opposites cancel, so we do want to put the moles on the bottom here. And the grams, which is 461 up on top of our PbI2. Again, multiplying the top, dividing the bottom will cancel out the moles. And we will be left with, and I'm going to multiply by the entire number, not the rounded number there, the 0.00377. And that's going to give us about 1.74 grams. Maybe I'll come up here. 1.74 grams of PbI2 would be produced in this case. So again, hopefully you kind of see a pattern. It is these same 4 steps over and over. Once again, I did it step by step and got some answers. You again can do it all in one calculation. Yeah. Yeah, so the single is really just without the intermediate. So if we do, let me just we'll do it here. So if you just did straight across, you would go 1.25 grams of what we started with, which was our PbNO3(2). The first step, right, is to convert to moles. So we'll use our molar mass, which 331.2. I'll spit that out maybe. 331.2 grams per mole of PbNO3(2). And again, at this point, if you stopped, you would have the moles of the PbNO3(2). And at this point, this would be our third step, which is our mole to mole relationship from the equation, which in this case was 1 mole of PbNO3(2) gives us 1 mole of PbI2. Again, at this point, these two guys would cancel, and we're left with moles of PbI2. And the last step here would be our fourth step, which would be using the molar mass of PbI2, and that was 461. So 461 grams per mole of PbI2. Again, the moles would cancel. So this basically would be step number 2, step number 3, and step number 4 there. Again, here you would just multiply everything on the top, and anything on the bottom you would want to divide. Remember, if you set it up like this and you're doing multiple divisions on the bottom, as we talked about, is probably a really good idea to do them individually. Divide by the first number, hit equals, divide by the second number, hit equals, rather than trying to put it all into your calculator at once. You could put as many numbers as you want up on top into your calculator, multiply them, make sure you hit equals, and then if you have multiples on the bottom, hit divide by the first number, hit equals, divide by the second number. Because remember, if you try to put a lot of numbers in at once and you don't do the parentheses correctly, your calculator will do the wrong math. So again, here we ended up with what we got there, 1.74 grams of PbI2. Questions on that? By the way, this is a product. This is what is known as a theoretical yield. A yield is always a product and how much you make. The theoretical yield, as we'll talk about a little bit later on in this chapter as well, is the maximum amount of product that you could produce in this reaction based on the equation and how much you started with. So based on the fact that we started with 1.25 grams of lead 2 nitrate, if everything went perfect, there was no side reactions, you didn't drop anything, didn't lose anything out of your beaker, you in theory should get out there 1.74 grams of PbI2, and that would be your maximum amount of yield. When you actually do it in an experiment, as we'll talk about, that is what's known as the actual yield. And that leads us to something else we'll talk about, which is the percent yield. Any questions on that? So for me, I don't really care if you want to do it step by step and get an answer. Again, just a reminder, don't round too much if you do that. If you want to do it all in one calculation, it's all good. And remember, just dimensional analysis, opposites cancel is what you want to kind of think about. Other questions? All right, let's take a look at another one here. Let's try this one here. Methanol burns in air in the following equation. If you started with 209 grams of methanol, what is the mass? So we're looking for the grams of water you would produce. So I'm going to give you some numbers to help you out here. Carbon 12.01. Again, oxygen still 16. Hydrogen 1.008. I think that's everybody you need. All right, so take a few moments. Again, follow those 4 steps and get yourself to the answer there. Okay, so let's take a look, see how you're doing. So once again, here we have an equation. We're given one piece of information, 209 grams of methanol, which is this guy. We want to know how much water we will produce, which is over here. So this definitely is a stoichiometry problem. So the first thing we want to do is balance the equation. And it does look balanced, so we are check on that. Next thing we want to do is take whatever they gave us and convert it into moles, which we do need to do since we only have grams. So we will need the molar mass here of CH3OH. So again, we got 1201 for our carbon. We got a grand total of 4 hydrogens at 1.008. And we got an oxygen at 16. That's going to give us 3204, looks like. 32.04 grams per mole. So to start our calculation here, we'll go 209 grams of CH3OH. Once again, it's basically on top, so we will use our molar mass with the grams on the bottom so that they cancel per moles of CH3OH. Again, at this point, if we were to stop, we're in moles of our methanol. Once again, we're not interested in our methanol. We are interested in the water. So this is where the stoichiometry comes into play. So we want to look at the relationship between these two guys. And from the equation there, we can see that for every 2 moles of methanol I throw in there, I am going to get 4 moles of water out. So here, just doing it all in one calculation, we are going to go opposites. So moles of methanol are on top, so we do need to put the moles of methanol on the bottom so that they cancel, and the moles of water up on top. So this again is step number 2. This would be step number 3, which is the stoichiometry step from the equation. Once again here, the moles of methanol will cancel. At this point, we would lay up our calculation and we would be in moles of water. We do want grams. So once again, we do need to do step number 4, which is our molar mass there of water in this case. Little 1802, right? 1.008 for the hydrogens and a 16 for the oxygen. 18.02 grams per mole. Once again, going opposites, we got moles of water up on top, which means we want moles of water on the bottom and the molar mass in grams up on top. And that would be our 4th step. The moles will cancel. So again, here we're going to multiply everything up on top, divide by what's on the bottom. So 209 times basically 4 times 18.02 hit equals, divide by 3204 hit equals, divide by 2 hit equals. And you're going to end up with approximately 235 grams of water is going to be produced in this particular case. Any questions on that there? Once again, this would be a theoretical yield in this case. Yeah. Again, how much you produce. Yeah. Correct. So if your question is, do you have to take into account the coefficient that's there? When you do the molar mass, the answer is no. So whenever you calculate the molar mass, like we talked about, it should only be the formula by itself. Exactly. So you don't want to use it in both places. So, and that's really the definition of molar mass is grams per basically 1 mole. And 1 mole basically represents just the formula by itself. So you should never ever incorporate the coefficients in a balanced equation into the molar mass because that is incorrect. Yeah. Other questions? All right. Questions on basic stoichiometry type problems here. No. All right. So if there's basic problems, perhaps there's more unbasic problems there. All right, so the next thing we're going to talk about are limiting reagents. Some people call them limiting reactants. And when a reaction actually takes place, it does not always take place in a perfect sort of reaction. And what that means is usually there is some reactant that gets used up first. So there's usually some reactant that gets used up first, and there's usually a reactant that you have plenty of. Now, the one that gets used up first is the limiting reagent. And the excess reagent is the one that you have left over after the reaction. So you have plenty of the excess reagent. You'll even have some left over when the reaction is done. The limiting reagent is always the most important one in terms of how much product you will produce. So just a very simple explanation of that. If I have A plus B that needs to come together to make AB, and if A was my limiting reagent and B was my excess reagent, the problem here is as soon as A runs out, is there any hope of making any product at this point? There is no hope to make any more product because you have no more A to put in there. So it is always the limiting reagent that determines how much product you could produce. Now, in basic stoichiometry problems, we assume that if whatever we're given is kind of like the limiting reagent, if it is a reactant. If it's a product, we don't have to worry about it. But if it's a reactant, we kind of assume in a basic stoichiometry problem that if we're only given one piece of information about a reactant, that's probably our limiting reagent and the other ones are excess reagent. In a limiting reagent situation or problem, you actually do have to take a moment and figure out which one is the limiting reagent. And by the way, that does need to be done through a calculation. You can't just look at it and go, I think that one's the limiting reagent. So the good news is there's multiple ways that you could approach these type of problems. And we'll talk about a couple here. But one way that we can sort of approach this, as you can see here in this example, our O2 is the excess. We got plenty of them left over at the end of the reaction. As you can see, we still have some O2 left over, which tells us is our excess reagent. To do these sort of limiting reagent problems, you could still follow our 4 steps, which is balance the equation, convert to moles, do your mole to mole ratio, and then obviously our moles to some other unit. Now, if you're doing a limiting reagent problem, right about here, you will have to do a calculation to figure out the limiting reagent. And then once you do, you will continue on with the calculation with the limiting reagent. So right about there, you could kind of do a little calculation to figure out which one's the limiting reagent, and then you could kind of continue on with it. So that's one way you could do it. And let's take a look here. So let's just say we actually had this reaction here that we saw maybe earlier. We had this guy, 3H2 plus our N2 gives us our NH3 here. And let's just say, for example, that we were told that we started with 2 moles of H2 and 6 moles of N2 in this case. So let's just say we started with that amount. Obviously, to get to those numbers, we might have had grams and used the molar mass to calculate, obviously, the moles. So we would have done step 1 already, which is balance the equation. We would have converted these guys into moles. Again, we could have started with grams in this case and got to moles. Now, here I would want to figure out which one is the limiting reagent. Now, how do I know I need to do that? If you look at this problem versus the ones we just did, I am given information about both reactants here, and I have enough information to get to moles of both reactants. So that is the thing that you want to look for in a problem, to know that at some point you should figure out the limiting reagent, which is if you are given enough information, whatever that information is, and you could calculate directly from that information the moles of each reactant, then it's a limiting reagent problem. If you're just given information about one of them, it's not a limiting reagent problem. You don't have to worry about it. But if you definitely could get the moles of each reactant, that is the big thing, that this is a limiting reagent type situation. Now, once you identify this as a limiting reagent type problem, we're at really step number 2 here. We have to figure out which one is our limiting reagent. So one way that you could do that is to just do a very simple calculation between the 2 reactants. And what you want to know is, if I want to use up all of my H2, how many moles of N2 is needed? So we're just going to do a very simple little calculation between the 2 reactants. So what I'm going to do is go, all right, if I take my 2 moles of H2, I'm going to use the mole-to-mole relationship between H2 and N2, which is 3 to 1. So again, for every 3 moles of H2, I got 1 mole of N2. You can go opposites here. So 3 moles of H2 on the bottom, 1 mole of N2 up on top. Moles of H2 will cancel. Gonna go 2 divided by 3 is 0.667 moles of N2 is needed. All right, so what I just did here is basically figure out, if I want to use up all my H2, how much N2 I got to put in there. Now I need to compare. So what should I compare it to? I should compare it to the starting amount of N2 I have, right? So I have 6 moles of N2, and I only need 0.667 moles of N2 to use it up. Do I have enough in this case? I do. I have 6 and I only need 0.6, right? So yes, I have enough. And because I have enough, what that tells you is, in this particular case, the N2 is your excess reagent, and by default, your limiting reagent would be your H2 in this case. Now, does it matter which one you choose? It doesn't. You do not need to do both of these calculations, but if you chose the other one, let's say you want to know if I want to use up all my N2, how much H2 is needed. So you could do the calculation for either reactant. And if I did it this way, I would start with my N2, which is 6 moles. I would use my same mole-to-mole relationship flipped. 1 mole of N2 gives me 3 moles of H2. Moles of N2 cancel and tells me I would need 18 moles of H2 is needed. When I compare my 18 moles of H2 that is needed to how much I have to start with, which is only 2 moles, I do not have enough, right? So I do not have enough. And what that tells me is the exact same thing the other calculation told me, that the H2 is the limiting reagent and the N2 would be the excess reagent. So you could choose either one to do that simple little calculation between the two reactants, and you can then figure out which one's your limiting reagent. Once I know that the H2, for example, here is my limiting reagent, I would then do my rest of the calculation using the limiting reagent starting amount. So if I want to know how much product, I would go with my 2 moles of H2, which is my limiting reagent. I would then do my mole-to-mole relationship between H2 and NH3, which is 3 moles of H2 to 2 moles of NH3. The moles will cancel. I then could use the molar mass of NH3, 1703 grams per mole. The moles will cancel. This is basically step number 3 and step number 4 there. And that would tell me that in this particular made-up example here, 2 times 2 times 1703 divided by 3, I would produce about 22.7 grams of NH3 in this case. That would be my theoretical yield. Yeah. Any questions on that there? Now, another very common question that you're sometimes asked in limiting reagent problems is, how much of your excess reagent do you have left over? So we could also answer that question based on these calculations that we did to determine our limiting reagent. So we already know that the N2 was our excess reagent, and we did this calculation to figure out that to use up the limiting reagent, I need 0.667 moles of it, and I have 6 moles of it to begin with. So we could actually figure out how much of that excess reagent will be left over by taking the moles of my excess reagent that I started with, which was 6 moles, and subtract it from the moles that was needed to use up the limiting reagent, which was 0.667 moles. And that would tell me that at the end of this reaction here, I will have approximately 5.333 moles of N2 left over. And if you want to know how many grams that would be, you can use the molar mass of N2 and figure out how many grams that would be as well. So those are very common questions: how much product you reproduced, which should be based off the limiting reagent, and how much of the excess reagent is left over. Any questions on that there? Now, you do have to, like I said, you do have to do a calculation to determine the limiting reagent. It is not always the smallest number of moles, although a lot of times it is. It is not always the smallest number of moles. So you cannot just go by like that one is the smaller number of moles. That will not work every single time. So you do have to do a calculation. So this is one way that you could do limiting reagents. The other very popular way nowadays that people are taught is to do two separate calculations, one from each reactant to the product, and whichever one makes the smallest number of product is your limiting reagent and your theoretical yield, which is perfectly fine as well. You could kind of take that approach if you want. An alternative approach, which I think is much, much better, is you could actually do what is referred to as sort of like an ice table calculation. And an ice table calculation is actually a calculation that makes it pretty easy to answer all types of questions very quickly. So let me show you how to do that one as well. And we'll just use this example here to kind of show you how to do it. So one way you could do is what I just showed you, obviously, do that calculation in between the second and the third step to figure out the limiting reagent and just continue on through the rest of the steps. You could again do two individual calculations, one from each reactant to the product, whichever one makes the smallest number of grams of your product is the limiting reagent and also your yield. But let's say we did this problem here. 3H2 plus Rn2 goes to our 2NH3. And we're going to do what is known as an ice table approach. And you may like this one better. And if you're planning on taking 200B, this is pretty much the calculation that you do the entire time. So be like a preview, I suppose. It might not look so weird to you when you get there. By the way, I means initial. C means change. And E in this case will mean end. When you go to 200B, it will mean equilibrium, basically. But we'll use it as end in this case. So the first two steps of any approach that you take are pretty much the same, which is you need to have the equation balanced and you need to convert things to moles. So those two steps, no matter which approach you take, pretty much everybody's got to do those two steps. So once you have it in moles, we're going to do our initial part here. And again, I'm just going to kind of steal the one we did here, which was 2 and 6. So we're going to have 2 moles here of this guy and 6 moles of this guy. And you could safely assume 0 to start with on the other end. Now, the change in ice tables are usually represented by the letter X. Now, when this reaction occurs, this reaction is going to occur and it's going to go from left to right, right? That means the amount of our reactants, which is on the left-hand side, should they be increasing or decreasing? They should be decreasing, right? And our products which are being made should be increasing, right? So the way we represent that in an ice table is with minuses and pluses. So on the left-hand side here is going to be minus x's, and on the right-hand side it's going to be plus x's. So this would be minus 3x, and the 3 is actually the coefficient, which is super important when you do an ice table, because that 3 does the mole-to-mole relationship for you. It does the stoichiometry for you. So you do have to use the coefficient. This will be minus x because that's a 1, right? So it's basically 1x. And this would be plus 2x, which is over here. Now, when we get to the end here, we're just going to bring everybody down. So we got 2 minus 3x. I'm going to get rid of the moles so it's not too crowded there. And 6 minus x and 2x, right? So at this point, when you do this table, you can now determine which one's your limiting reagent. And the way we determine which one's the limiting reagent is we're going to set each of these guys equal to 0 and solve for x. So this one's pretty simple. Just move the x to the other side. X is equal to 6 moles, by the way. So that's what that represents. If you do this, the 3x goes to the other side equals 2. Divide, and you end up with 2 divided by 3, which is our x is equal to 0.667 moles. So you could do this really quick sort of algebra calculation super quickly. And the one that is the limiting reagent is the smallest. X is your limiting reagent. So that would mean, just like we found out in the last calculation, our H2 is our limiting reagent, and our N2 would be our excess reagent by default, which means we don't really need this number anymore. Okay. Now, why is this sort of beneficial? This is beneficial because very quickly you could pretty much answer any question that may be asked of you. This X value is this X value. It's that X value, and it's also that X value right there. So you basically could put that X value in really quickly, and all you have to do is go, oh, I want to know how much product. So NH3 at the end equals 2 times X, which is 2 times my X value of 0.667 moles. And that will give me how many moles I have. So 2 times 0.667, 1.334 moles of NH3, a little molar mass of NH3 like we did before, if we want grams. And now I very quickly sort of figured out my 22.7 grams of NH3. Benefit of this is you don't have to go back to the beginning to do the how much is left over of our excess reagent, because I know this is my excess reagent, and I know at the end my excess reagent, which is N2, is 6 minus my X, which would be 6 minus my 0.667 moles. And that very quickly will now tell me 6 minus 0.667. I have the 5.333 moles of my N2 left over, which if we also wanted grams, again, we could just use the molar mass of 2802 grams per mole. And that will tell me that I have left over about 149 grams of N2 left over in that case. We obviously started with 6 moles of it, right? And we had 5.33 left over. By the way, if I put it into here, which is my limiting reagent, it should probably equal 0, right? Because it should all be used up. Yeah. So this ice table approach is a really good approach because you can very quickly, as soon as you figure out that X value, figure out how much product you have. In the case of this one, we only had one product, but we could have had 2 products, which means I could very easily figure out how much of each product I produced. I could also very quickly go back and figure out how much of my excess reagent is left over. Any questions on that? So that is 3 different ways that you could do these. I don't really care which one you like, yeah. But again, you will see ice tables if you take 200B, so maybe it'd be a good way. And it is a pretty quick way you can kind of get to all the answers that you're typically asked. Any questions? All right, we're laid up there for today.